first homework assignment. This would be one of the official ones. Okay, now last time we were tackling the problem of how to solve electrostatics problems when we didn't know the charge distribution, but you did know the voltage on a whole series of conductors. And we had decided that we defined the voltage as the potential energy per charge. We had then observed that the electric field was minus the gradient of the voltage. And that, coupled with the first Maxwell equation, had meant that the electric field obeyed Poisson's equation, which could be written in the form del squared V is equal to minus 4 pi k rho. We then set out to solve the problem in which the charge density was 0 everywhere except on the conductors. That meant that we had to solve what's known as Laplace's equation, which was that, which is one of the fundamental differential equations that occurs in physics. There are 4 of them that will occur repeatedly. This is the first one we've encountered. Now, that being a differential equation, there are arbitrary constants involved. If it was an ordinary differential equation, they would be constants. If it's a partial differential equation, they are functions. Now, it turned out that the boundary conditions necessary for that to have a unique solution were knowing the voltage everywhere on a closed surface, or knowing the electric field everywhere on a closed surface, or some combination, so that all of the closed surface had one or the other known. If it was the second one, with the electric field everywhere on a closed surface, then you got the voltage to within an arbitrary constant. But that was fine. Since the electric field was the gradient, the constant would go away. So we set out to try and solve that equation given the boundary conditions, namely knowing the voltage on this closed system of conductors. So we observed that there are 2 aspects to the problem. One is solving that equation, which will have arbitrary functions in it. And second, applying the boundary conditions to determine what those functions are. We said that it's only easy to solve that equation. In fact, it's only possible to solve it analytically if the function v can be written as a product of functions of one variable only. We call that a separable equation. And what we meant by that, if, for example, we used Cartesian coordinates, then v would be a function of x, y, and z if it's Cartesian coordinates. And by separable, we meant that that function could be written as a product of functions of only one variable. Now that's a very special situation. In general, that isn't the case. The solution might be sine of x, y, z. That is not the product of sine x, sine y, sine z. So in general, this isn't the situation. But since we have these uniqueness theorems, that if we can find a solution that satisfies the boundary conditions, we got the total solution. It's okay to guess that this will happen and hope you're lucky. Now it turns out that there are a large number of coordinate systems for which that choice will indeed solve the equation. All of the ones that are normally interesting fall into that category. Rectangular coordinates, spherical coordinates, cylindrical coordinates, all can be written as products of one variable functions. Okay? Now, the difficulty is that it'll only be possible to satisfy the boundary conditions in a simple way if the symmetry of the problem matches the coordinate system. And so to see why that happened, we looked at a particular case where we had a cubic box made up of conducting sides, and we looked at the interior, the electric field, when to find the electric field, the voltage, and then the electric field, in the interior of this box. So the closed surface consisted of the sides making up the box. We chose to do a problem in which all the sides were at voltage 0 except for 1. Okay? Then, when we solved these equations, this became d squared v dx squared plus d squared v dy squared plus d squared v dz squared is equal to 0. That's just writing del squared in terms of Cartesian coordinates. And then we tried that. We guessed that would work. And when we did that and substituted it in, we got y times z times d squared x dx squared plus x times z d squared y dy squared plus x times y d squared z dz squared was equal to 0. And then we simply divided by x, y, z. And when you divided by x, y, z, this became d squared x dx squared times 1 over x equals 0. And then we observed that since this is a function only of x, only of y, only of z, the only way that that sum can equal 0 for all values of x, y, and z is if each of those individual terms is a constant. And so we made these constants beta squared, gamma squared, alpha squared, and the sign of this, whether we put a plus or a minus on these things, depended on the boundary condition. And this is where the fact that the symmetry of the problem matches the symmetry of the coordinate system became important. In our case, we had taken a system like this, placed our box with one corner at the origin and then sides L for our cube. And we'd said, okay, we're going to make the voltage 0 on all the faces except at x equal to L. So V equal V0 at x equal to L, and V equals 0 on all the other faces. All right? So then we looked at the equation for y. And we knew that the solution to this equation, which becomes d squared y dy squared, is plus or minus beta squared y. If you took a plus sign, you got exponentials. If you took a minus sign, you got sines and cosines. And we needed to have the function 0 at y equal to 0 and y equal to L. Exponentials won't do that. They can be 0 at one point, but not at 2. But sines and cosines are periodic. And so you can make it 0 at both points easily. And in fact, if you use signs, then the sine of 0 is 0. To make it 0 at the other face, all we had to do was make, so that meant we needed to use the minus sign, so we would get sines and cosines. And we had then a solution that looked like y is some constant times the sine of beta y. And now if we wanted it to be 0 at y equal L, we had to have beta L equal some integer number of pi's, because the sine of 0, pi, 2 pi, 3 pi, 4 pi are all 0. So that meant beta had to be equal to some integer number of pi's over L. And so we ended up with a solution for y, which looked like n pi over L times y. Now, that worked because the symmetry of the coordinate system matched the symmetry of our problem. Well, z was the same thing, because we had to have the voltage 0 at z equals 0 and z equal L. So that gave us z was equal to some constant, call it b, sine of some other integer, m pi over L times z. And that left us the x faces. Now, since these have now become minus signs, then this has to be a plus sign so that the 3 will add up to 0. And if this is a plus sign, it meant the solutions were exponentials. And we could write them as a e to the x plus b e to the minus x. Or it's more convenient to define a combination, namely the hyperbolic sign, e to the x minus e to the minus x over 2, and the hyperbolic cosine, e to the x plus e to the minus x over 2. Those are just linear combinations of e to the x and e to the minus x, so I can use those just as well as e to the x and e to the minus x. But this is the right combination to use because I need to make the function 0 at x equals 0. And in order to do that, I need to have equal numbers of e to the x's and e to the minus x's, so they'll cancel out. And so if I do it in terms of this, it'll be easy to satisfy the boundary condition. And so what we'd said is that the solution for x must look like some constant times the sinh of alpha. But alpha, from this, we had alpha was equal to the square root of beta squared plus gamma squared. And therefore, we got the sinh of the square root of n squared plus m squared to the 1/2 pi over L times x. Okay, now that had the virtue that it made that x equal to 0 at x equal to 0. And so that's where we got last time. We had decided that our solution, v of x, y, and z, was some constant times the sinh of n squared plus m squared to the 1/2 pi over L times x times the sine n pi over L times y times the sine m pi over L times z. And that had satisfied 5 of the 6 boundary conditions, but not the 6th. So to satisfy the 6th, what we said is, well, if that's a solution for one value of n and m, then it's a solution for any value of n and m that are integers, and I can add them together. Because if v1 is a solution of that equation and v2 is a solution of that equation, then the sum is. Because the derivative of the sum is the sum of the derivatives. Is that okay with everybody? So, our conclusion was that we could write this as a sum over n and m of a, n, m, where these go from 1 to infinity. And that was the general form. Now we have to see if we can choose the a's such that this is equal to v0 when x is equal to L. Making sense? So that's where we're at. So let's see if we can do that. So what we must have is v0 is equal to the sum n, m, a, n, m, sinh of n squared plus m squared to the 1/2 pi L over L is 1, so just pi, times the sine n pi over L times y, sine m pi over L times z. So, question is, how can we choose a and m to make that true? Well, there's a standard procedure for doing this, which you will encounter over and over again in physics, and that is what we're going to demonstrate now. These guys, sines, have an interesting property. They are what is called orthogonal, meaning that the integral sine nx sine mx dx from 0 to 2 pi, which is the period of the sine function, is some constant if n is equal to m, and 0 if n is not equal to m. Now when you have functions like that, when you have a family of functions, in this case sine nx, if those functions have the property that if n is not equal to m, you get 0, and if it is equal to m, you get some constant, you call those orthogonal functions. It is very similar to taking a vector and splitting it into components. There, the components are perpendicular to each other. Ax, x hat, x hat and y hat are perpendicular to each other. Well, here we have functions that are in this sense perpendicular to each other. And when we come to do quantum mechanics at the end of this semester, we'll find that the state of a system, what it is in, what for an atom, for example, what's the ground state of the atom? We'll find that any system can be thought of as a superposition of other states For example, a system which has a definite energy could be thought of as a superposition of states which had definite position. And those states will be functions. And we will have a series of orthogonal functions. So this is a concept that's going to appear over and over again in physics. Now, right now, those just sound like words. We're going to use them now, this idea, to solve our problem. And after you've done a little of this, it'll begin to be more than words. It'll begin to actually have a physical significance for you. So we're going to use this fact. Now, we need to determine what alpha is. I mean, this is an easy integral to do. You can look it up in any of the tables. And when n is not equal to m, when they're integers, you get 0. If they were equal to each other, this would be the integral of sine squared. All right? And what is the integral of sine squared from 0 to 2 pi? Well, that we can work out, because what is the average value of sine squared over a period? Mm-hmm. This is some number we're going to find. And what it says, if n and m are not the same, you're going to get 0. If n and m are the same, you obviously won't get 0 because you'll be integrating sine squared, which is always positive. And therefore, you obviously won't get 0. Oh, I see what you're saying. This is equal. Yeah, sorry. I'm sorry. Well, sine squared has an average value of what? A half. Why? Because you know that sine squared plus cos squared is 1. And sine squared and cos squared are the same. Average values are the same. And so each one must be a half. So the average value of this thing is a half. If we integrate over a range 2 pi, then that integral must be pi. Right? So that is pi. All right. Now, let us use that fact on this equation. And so what I'm going to do is I'm going to multiply both sides of the equation by sine n prime pi over L times y, sine m prime pi over L times z. And then on the other side, I will have summation n, m, a, n, m. And now I'll group them together. This will be cinched m squared plus n squared to the 1/2 times pi times sine n prime pi over L times y, sine m prime pi over L times y, times sine sine m prime pi over L times z, sine m pi over L times z. I just multiplied both sides by this. Now I'm going to integrate both sides. From y prime equal 0 to L and z prime equals 0 to L. So So I'm going to put in here, put the a and m over here, and then I do the integral. Y prime equals 0 to L. Z prime equals 0 to L. That's all okay, because I've done the same thing to both sides of the equation. Following so far? Now let's perform the integral on y prime over here. So I have sum n m a n m cinch n squared plus m squared to the 1/2 pi. Now, when I perform this integral, let's make a change of variables. Let squiggle equal pi y divided by pi y divided by L. Okay? Now, that means that d squiggle is equal to pi over L times dy. And so when I have this thing, this will become n prime squiggle and n squiggle. And I will have to multiply because I'm integrating these things here. dy dz, and integrating here dy dz, I will get, because of this, an L over pi times d squiggle. And so I'm going to do this for both the y and the z terms. And so that will give me L squared over pi squared times the integral on, these are y's and z's, the integral from squiggle equals 0. Now, I'm going to integrate to L. And when I integrate to L, this makes this just pi. So, 0 to pi, integral something else, 0 to pi, times sine n prime squiggle, sine n squiggle, d squiggle, sine m prime sine m squiggle, that. Okay with everybody? Can't read it, so let me write it bigger. Sine m d-eta. Now, I know how to do this integral because that is the integral that I had up there. It's going to be 0 unless n prime is equal to n. If it is equal to n, then it's the integral of sine squared from 0 to pi. That's 1/2. That'll be pi over 2. And so performing this will give me n, a, n, m, cinch, n squared, m squared to the 1/2 pi, L squared over pi squared, But each of these integrals is going to give me a pi over 2. And so I will get pi squared over 4. And then I will have 0 or 1. 0 if n prime, let's put it this way, 1 if n prime equal n, m prime equal m, 0 otherwise. So I've taken this sum and I've reduced it to one term, the term that has n prime equal n and m prime equal m. Making sense? So this sum then is a n prime m prime times the hyperbolic sinh of n prime squared plus m prime squared to the 1/2 times pi. So that is the right-hand side of this equation, which means if I evaluate the integral on the left-hand side, I will be able to determine a n prime m prime. So let's put those two things together. And what do we have? We go back now to that thing. And so the left-hand side is v0. Now, I'm going to make the same change of variables I did before, since I'm integrating over the same variables. And so that will mean that I want to make this change, which means that the dy becomes L over pi e squiggle. There are two of them. So I get L squared over pi squared times the integral squiggle equal 0 to, it'll be just like it was before. So it'll go to 0 to pi. Integral eta equals 0 to pi of that product of signs. And so what we have is sine n prime eta sine m prime Okay, everybody following so far? This is the left-hand side. So now do this integral, the first one. v0 L squared over pi squared. Now the integral of sine is minus cosine. Over eta prime. Evaluated between 0 and pi. Now do the integral on this one. And that will be, again, minus cosine m prime over m prime evaluated between 0 and pi. All right. Everybody following so far? So what is this? Well, there are two cases to consider. Suppose n prime is even. Then this is things like 0, 2 pi, 4 pi, 6 pi, 8 pi. And all of those things are 0, right? The cosine of, all those things are 1. The cosine of 8 pi, 6 pi, 4 pi, 2 pi, they're all 1. The cosine of 0 is 1. So when I subtract them, I'm going to get 0. So if either n prime is even or m prime is even or both, I'm going to get 0. So n prime and or n prime even implies you get 0. Now suppose they're both odd. Well, if they're both odd, then what's going to happen is you're going to have cosine of, so if it's odd, suppose it was 1, for example, you would take out the two minus signs, and then you'll have cosine of pi minus cosine of 0 divided by 1. Or if it had been 3, it would have been the cosine of 3 pi minus the cosine of 0 divided by 3, and so on. Now that's minus 1, that is 1, and so what you get is minus 2 divided by 1 is just minus 2. And the same thing is here. So for a given value of n and m, then you are going to get 2 twice, 1 from each of those. So you get b0 4 L squared over pi squared. And then you have n prime, m prime in the denominator. So that is the left-hand side of the equation. Everybody followed that? That must be equal to what we got over here on the right-hand side, which was a n prime, hyperbolic sinh of this. I've missed an L squared over 4 here because the pi squared cancels, but I had L squared over 4. Sinh of n prime squared plus m prime squared pi times L squared divided by 4. So we can now solve for a n prime, and is equal to v0 times 16. The pi squareds are here. The L squareds cancel out. N prime, sinh of n prime squared plus m prime squared square root times pi. Okay? So we have determined the coefficients in that series which are required to satisfy the last boundary condition. And so now we have the problem completely solved. V of x, y, and z is equal to the sum over n and m of v0, 16, pi squared. Let's factor that outside the sum, because it's just a constant. So we have 16 v0 over pi squared, sum n and m odd from 1 to infinity of the sinh of n squared plus m squared square root pi over n times m times the sinh of pi over L n squared plus m squared square root x times the sine n pi over L times y times the sine of m pi over L times z. So we have now found the potential everywhere on the interior of this conducting box with specified voltages. In other words, using this procedure, we can solve any electrostatic problem because we have two situations. Either the charge density is known, or it isn't known, but the voltages are. If the charge density is known, we do the integral that we looked at the other day. If the voltages are known, we solve that equation. The problem is, in general, for arbitrary shapes, you can't solve it analytically like this. You have to do a numerical calculation, but you can do that. We're doing especially simple cases where the symmetry allows us to solve it. I know the words especially simple doesn't seem to apply to this, but compared to the alternative, it is. They won't be, no. Okay. Now, the voltage is not what's interesting. What's interesting is the electric field. That was the whole idea here, was to find the electric field. How do we find the electric field now that we got the voltage? The electric field is minus the gradient of the voltage. So, to find the electric field, all we have to do is take minus the gradient of this. And what is that? Well, we better have a new board for this. Since we're now at blackboard number 5, this is rapidly getting out of hand. Reminds me of a professor I had in graduate school who was described as having a constipation of ideas and diarrhea of the chalk. Well, this is getting to look like that. So, what we got to do is take the gradient of this thing. Well, that's not as bad as it sounds. Because what is the gradient in the coordinate system we're using, which is Cartesian coordinates? It is minus x hat d by dx minus y hat d by dy minus z hat d by dz. So, what is the x coordinate, x component of the electric field? It is simply take the derivative of this thing with respect to x. Well, what depends on x? Only this. So what we will get is minus 16 d0 over pi squared sum n m cinch n squared plus m squared to the 1/2 pi n m. I won't affect either of the signs, so they'll stay the same. Sine n pi y over L sine m pi z over L. Now, the derivative of sinh, remember, sinh was e to the x minus e to the minus x over 2. So its derivative, you would get 1/2 e to the x plus e to the minus x. And that's cosine. So the derivative of sinh is cosine. And so we will have hyperbolic cosine of pi over L x m squared plus n squared to the 1/2. And then I have to multiply by that and that. So pi over L m squared plus n squared. So that will be the electric field. And similarly, to find the y component, I take the derivative of sine, which will just give me n pi over L times cosine, and similarly for z. So once you got v, it's an easy matter to get the electric fields. All right? Now, in the end, although the math looks complicated, the ideas are simple. So let's apply our physical intuition to answer some questions about that solution. Let's ask ourselves, what is the electric field E at a point L over 2, L over 2, L over 2. So it's the center of the box. What must be the y component of the electric field at the middle of the box? Don't look at the equation, just ask yourself physically, what must it be? Must be 0, right? Because the two y faces were at 0, and you're right in the middle between them. So anywhere along the line that was parallel to the y faces going through that center, the electric field had better be 0. Okay? Now, how would that come about? Take the derivative of this, that sine would turn into a cosine. At the center, you have L over 2. And so you would have the cosines of an odd number of pi over 2s. Pi over 2, 3 pi over 2, 5 pi over 2. The cosines of all of those things are 0. Right? Similarly, for the z-axis. If you go halfway between the z plates, you'd better get 0. Right? Okay, now how in practice would you find the electric field at a given point? You evaluate that sum. Now, how does it depend on n and m. Well, you're going to have square roots of these things, which are going to give you something of the order of m. Means the whole thing is going to go down as 1 over n or 1 over m. And so as you go up to larger and larger n's and m's, the contributions get smaller and smaller. And so you expect the field to, this sum to converge. Okay? So in practice, what you have to do is simply evaluate this thing until the adding additional terms don't change the result by more than the accuracy you're trying to get. Make sense? Now, one of the homework problems I've given you involves doing this. A slightly different situation that will require you to think a little bit about this. Don't want you dying of boredom here. You have to think about it a little bit. All that I've done is I've shifted the origin of the box, and I put voltages on 2 of the faces instead of on 1. How do you think you would solve that? Forget about the shifted origin. Just look at the 2 voltages on 2 faces. If you have a solution, 2 solutions, the sum is the solution, right? So you would solve it by solving 2 problems. One in which there's a voltage on one face, the other with the voltage on the other face, add them together. And that'll be a solution which has V0 on 2 faces rather than 1 face. And if you want to shift the origin, same rules apply, except now you have to have the sign at minus L over 2 and plus L over 2 if you put the origin at the center of the box. So that just means you have to choose the alphas, betas, and gammas a little bit differently. But it's the same procedure. So I'm giving you a slightly different problem just so you can get familiar with how to do these things. Okay, the general idea making sense? You see what went on here? So we now, in principle, know how to solve any electrostatic problem that involves conductors. Next time, we're going to look at some more special cases. This is all we're going to do with Laplace's equation. And we'll go back and we'll find out what V is for given charge distributions where you know the charges. You're terrified? Good. You should be at this point. But you should become less terrified as time goes on. Switch Thursday and Friday this week.